All right, hello AP Chem students and welcome to topic 2.2, intramolecular force and potential energy. So our learning objective here is 2.2.a, which is represent the relationship between potential energy and distance between atoms based on factors that influence the interaction strength. So let's dig into that. So when we're modeling bond length, the length of the bond in nature is determined by the balance between the repulsions and attractions of charged particles and the kinetic energy due to motions of electrons. So the atoms are going to settle in a distance that provides the lowest, and in this case, lowest is always going to be most negative potential energy. So we can observe that using a potential energy graph, which looks like this. So this graph is going to show the potential of the bond versus distance between the atoms. And then we can typically look at several different positions on this graph. So I want to show you that in a little more detail on the next graph slide here. So in thinking about bond length, we kind of have four scenarios, okay? So in scenario one, and these are actually numbered backwards of how I would do it, but there you go. So here you go. Here's scenario four. In scenario four, the nuclei are too close together. And so they're going to repel each other because those nuclei come too close together. You've got that strong positive charge on the nucleus, and it's just going to repel. And those atoms are too high of an energy. This is not at the bottom, and so this is not the optimal bond length. Your lowest point on your curve is the optimal distance between the nuclei, and this is what is seen in nature. So this is kind of where things balance out, all right? So the nuclei are spread far enough apart that the nuclei are not repelling each other to the point that they're doing what we saw in picture 4 here, but they're close enough together that the atoms are actually interacting and forming the bond. So this point here, which on this graph is an energy of negative 432 kilojoules per mole, and a bond length of 74 is the optimal bond length in what we observe in nature. Now in diagram 2 here, our nuclei are farther apart, but they are too far apart. And so there's less force, a la Coulomb's law, right? The distance is too far here. And so there is not the interaction that is required to form the bond here. And so this is not where we see the bonds settle either. And then in situation 1, the nuclei are very far apart. And in this case, they're not even interacting. Okay. So that's where like these atoms are just independent of each other completely. So let's think, this graph also demonstrates bond energy, which is the amount of energy that's required to break a bond. So we're going to come back to this concept more when we get to thermodynamics. For right now, you just need to be able to find this position on the graph. And it's always going to be here at the bottom of the curve. Okay, so let's apply Coulomb's law to bonding. So just a reminder that Coulomb's law is on the equation sheet. It is here in the atomic structure section, and you will not have to do calculations with Coulomb's law. You will need to apply it for proportional reasoning, as you see here. Okay, right? This alpha sign means is proportional to. So Coulomb's law applies to bond energy and length in ionic bonds in particular. So stronger bonds, well, you can think about it between the electrons and the nucleus as we just did. But when you're thinking about ionic bonds, the stronger bonds will be between smaller size atoms and larger charges. So we want, if this term up here increases and this term down here decreases, then we see this force increase. But Coulomb's law is also at play with subatomic particles. So that's kind of my thought just a second ago. The repulsion between the neighboring nuclei and the attraction between the oppositely charged ions finds this happy medium, and it kind of balances out here at the bottom, which determines the length in the ionic bond. So the internuclear distance that minimizes the potential energy is the spacing that we observe when we measure bond lengths of ionic bonds. And by the way, we tend to measure the lengths of these bonds by putting them in a crystal lattice in solid form, and we're going to get to ionic solids in actually topic 2.3. So that's coming up next. All right, so let's look at some bond lengths here. So if we see the whole halogen series bonded with hydrogen, right? So then the smallest atom, of course, is going to be fluorine. Chlorine will be the next largest, and then bromine, and then iodine. So the bond length here is 0.917, and the strength is 136. And then you can see that as we go down the family and our atoms get larger, our bond lengths also get larger or longer, right? But our strength decreases. And that's because this force, when we increase your denominator, we decrease the force overall. So this is an application of Coulomb's law. So you can see that that is what is happening here. So then let's look at what the graph looks like if we're talking about an ionic bond, okay? So here's some takeaways from this graph, and they're very similar to what we just saw. Ions that are too close have a repulsion of the valence electrons in the nuclei, and we see a positive potential energy. And so that is not the situation that's going to form the ideal bond in nature. Ions that are too far apart do not have enough attractive force to hold the bond together. And so this potential energy is too small in terms of it's not negative enough. All right. So the magnitude is too small. It's a small negative potential energy. Okay. And then the optimal distance is the most negative potential energy. And that's what we see right here. So this is where, if we measure this in nature, this is the bond length that we observe between sodium and chloride. Okay. So bond order. When we're thinking about covalent bonds, another way to further classify the bonds is by using bond order. So we don't see bond order in ionic bonds because ionic bonds are a different kind of bond. They're formed by the attraction between the charges. With covalent bonds, we have overlapping electron clouds and sharing of electrons. And what can actually happen is we can share more than one pair of electrons. And we're going to get more into this later in this unit. So we're just kind of introducing this idea of bond order and multiple bonds right now. And then we're going to come talk about this much more with Lewis structures, which I believe is section 2.5. So let's talk about this. So if we look at some pictures up here, okay, so here we have ethane, so 2 carbons and then the surrounding hydrogens to fulfill its octets. This is ethene, where there's a double bond between the 2 carbons, and then that, of course, removes 2 hydrogens because carbon can only form 4 bonds. And then this is ethine, which has a triple bond, all right? Now, organic is not part of AP chemistry, and you would not need to know these names, but what is fair game in AP chemistry is for them to use structures like this that they show you to ask questions about topics that you would be expected to know, such as bond order. So the type of bond shown in this picture here is a single bond, and that is an overlap of just one pair of electrons. So 2 electrons are being shared here. In a double bond, we see this denoted as 2 lines. This is 2 pairs being shared. In other words, there are 4 electrons that are being shared among these 2 carbons. And then we have a triple bond, and that is 3 pairs of electrons being shared. So 6 electrons overall being shared between these 2 carbons. So then these bonds then translate to bond order. So a single bond is a bond order of 1, a double bond has a bond order of 2, and a triple bond has a bond order of 3. So these are whole number bond orders. You can actually have fractional bond orders. We're going to talk about that when we get into resonance, which is in section 2.6. So you can see that we're kind of, building these concepts on each other as we go through this unit. So in thinking about the relative strength, a single bond is going to be the longest. A double bond is going to be in between, and then a triple bond is going to be the shortest. So if you're thinking about comparing similar structures here, single is longest, and then you've got this middle double bond, and then a triple is going to be shorter. Then the strength mimics that as well. A single bond is going to be weakest, a double bond is going to be in the middle, and then a triple bond is going to be the strongest. Okay, so again, you can assign bond order strictly by looking at the number of bonds that share between 2 atoms. And then you can see this bond length and bond energy relationship again. Okay, so here's a longer bond, and it has less energy. Here is a mid-length bond, and it has more energy than the single bond. And here's a triple bond, which is the shortest, and then the energy increases. And so that's the same thing that we saw back here, right? Okay, so nope. If I go way back here, okay. So the shortest bond was the strongest. Okay, so this is not a new concept. All right, so scrolling, woohoo, here we go, back through my PowerPoint. And then you can see that this is true not just for carbon, we also see it in nitrogen. And we see it in everything like this. We see this repeating pattern of this single, double, triple bond order of 1, 2, 3. So again, bond order 1, 2, 3, 1, 2, 3. So what should I be able to do with this right now? So you should be able to examine a potential energy versus distance graph to determine the bond length and the bond energy for a designated bond. Again, you're just going to go to the bottommost point of your curve. You're going to identify the bond order of a bond, single, double, and triple, just with a 1, 2, and 3, and compare the relative strength and length of single, double, and triple bonds, where single are the longest and weakest, and triple are the shortest and strongest. And then apply Coulomb's law to compare the strength of given bonds with that, again, you want to be able to think about the length of the bonds and also the magnitude of the charges that are in the bonds, particularly when you're looking at ionic bonds. So for example, sodium chloride would not be as strong as magnesium chloride because sodium is +1, whereas magnesium is +2. Okay, so that is it for this section. Our next section will be 2.3 when we talk about ionic solids. I'll see you then.